Hi, welcome to quantum theory, and we are focusing on modern atomic theory. This course discusses several basic aspects, which covers modern atomic theory, okay, periodic table and periodic properties, main group element, and until nucleus chemistry. And this learning objective has been discussed in one of my videos. Please refer to that. And we also have discussed regarding prior knowledge, and you can have a look at the series of YouTube links that will give you the information required for you to know as your prior knowledge before you can proceed with the next topic. So now let us discuss about history of atomic model. It is very important to understand the history in order for you to understand or to appreciate the evolution or the process starting from Dalton until Rutherford, as well as how we end up at Bohr. So according to Dalton's, okay, elements are made of tiny particles called atoms. So Dalton's is the one that find out about the atoms, but only he knew about it is as particles. Okay, then there is a small, very tiny particles called atom. Atom is one element can become atoms of one element can be combined with atoms of other elements to form compounds. So from your previous prior knowledge, you should know what is element, what is a compound. Okay, you should be able to differentiate between element and compound. Atoms are okay. This one is not important. Now, these are the postulates of Dalton's. All matter is composed of atoms. Okay, atoms cannot be made or destroyed. At this moment, probably we can just accept these postulates by him. All atoms of the same element are identical. Different elements have different types of atoms. Chemical reactions occur when atoms are rearranged. So these are all from Dalton's postulates. Okay. Okay, now we move on to the next scientist by J.J. Thompson. Okay, so Dalton has imagined that compound, okay, uh, is a combination of atoms. He find out about small, tiny particles called atom, and you know about his postulates. Huh? So J.J. Thompson, okay, has done an experiment by using what we call as cathode ray tube. Okay, let's discuss. And you can see after that, Rutherford comes in to have an improved version of atom structure. Okay, so let us focus on J.J. Thomson and Rutherford. Okay, so this is cathode rays by J.J. Thomson. Okay, so this is anode. Sorry, this is cathode, anode. Okay, and when the voltage here is set, okay, there's a stream of negative charges, okay, between this cathode and anode, okay. So when the voltage here is neutral, meaning that there is no negative or positive charges here, the stream of the negative charge from here goes right through in a straight line. Okay, but once we have a voltage is supplied and there is a positive and negative charge here, there is a deflection of these particles. So from here, J.J. Thomson conclude that these particles are negatively in charge because it is attracted to a positive pole, right? So these particles is later known, named by electron, okay? Now, J.J. Thomson further do the experiment by introducing a small amount of gas, okay? And from that amount of gas, positive charge species is produced, depends on the gas. And he found out that the deflection now is moving towards negative, okay? So he concluded that atoms, okay, contain both positive and negative particles, okay? So finally, he came up with what he called as a plum pudding model, okay? So the atoms contain a negative charge particles and positive charge particles. So he suggested that the negative and positive charge particle distributed like plum in pudding model, right? So this is what he suggested for atom, the model of atom. And after that, Rutherford's run an experiment, okay, after a while. Okay, this is what we call as gold foil experiment, okay? So gold foil experiment, this is the setup, right? This is the source of beam, and this beam producing alpha particles. So you should know alpha particles are positive particles, okay? They are positive particles, and this is the gold foil. And this is sort of a reader, or where uh, it recorded the particles when it hits the zinc sulfide fluorescent screen. So when the particles hit the fluorescent screen, then we can actually detect which actually whether it is deflected, whether it is passed through, or whether it is a small deflection here or highly with high deflection. Yeah? So you can see from this observation, you can see one, it passed through, okay? When you bombard alpha particles with, of course, the alpha particles is positive in charge, and you bombard through the gold foil, means there are atoms here, gold atoms here, and it goes through. Some actually goes through without any problem, just pass through, and you can see that it is recorded here. But some alpha particles probably mildly, a bit deflected. You can see there's a deflection. So it goes here, it doesn't go straight here. And some is strongly deflected. Okay, you can see that strongly deflected back, or not to say 180 degrees, but there's a big deflection of alpha particles based on the Rutherford's experiment or gold foil experiment. All right, so this is the same um, experiment. So what are the observations? Okay, most particles pass straight through, being said no deflection at all. Okay, so this is the metal foil, this is the alpha particles. So when you pass through, when you bombard the alpha particles, it goes straight. Okay, and second observation, okay, some were deflected. Some have small deflection, and some has very big deflection. Okay, so we can view. Okay, imagine this is the gold tin foil, and we have gold atoms in the gold tin foil. This is what happened when we bombard the alpha particles. Okay, some goes through, some small deflection, some very large deflection. Okay, okay, and okay, based on that observation, the conclusion, for example, most particles pass straight through means that the atoms are mostly empty space. That is the conclusion from this observation number one. The particle pass straight through implies atoms are mostly empty space. Some particles were deflected. So there's a big deflection means atoms, okay, must have a densely positive charge in the middle. Okay, so that will be the conclusion from the second observation. Some particles were largely deflected, and that conclude that there is a positively charged, okay, a condensed positively charged matter in the center of the atom. These are again diagrams showing the observation and the conclusion from the observation. This is very important for you to understand. Again, most of the alpha particles pass through, okay, because atoms mostly are empty spaces. The structure of atom consists of empty spaces, okay. Some minimum deflection, some has a very large deflection, meaning that they are somewhere in at the center of the atom there is a dense positive charge, so that it deflect the alpha particles. Remember that the alpha particle is positive, so highly dense positive deflect the alpha particle. Okay. So from here, okay, if you remember just now, J.J. Thomson find out about the electron as well as positive charged particles, okay, but he proposed a plum pudding model, meaning that he suggested that the negative charge particles is distributed uh, in a positive charge among the positive charge particles, like plum pudding model. But according to Rutherford's experiment, it seems that his suggestion, the J.J. Thomson suggestion of atomic model, is not accurate, because you can see here there's a lot of empty spaces and only certain parts has a densely positive charge. So this is the final what we knew about atoms that we know today. Okay, the atomic nucleus. Okay, the densely positive charge that Rutherford observed just now and make a conclusion consists of protons and neutrons. Okay, and surrounding. Okay, the atom is electrically neutral because it has balanced electrons, which is negative in charge, and nucleus, protons and neutrons, protons with positively charged, then it balanced, so atom is neutral. Okay, so you can see that this is cloud of electron. So this is the final version of atomic structure that we know today. And these are the symbol that you have to know when you are describing the atom or isotope. So X is atomic symbol, means whether you have, for example, sodium, calcium, magnesium, and A is the mass number. Mass number means it's a total of atomic number or proton number plus neutrons. Okay, so A is mass number. I think you should know on this matter. This should be in your prior knowledge. Okay, so isotope, atoms of an element with the same number of protons but different number of neutrons. As you know, neutrons does not contribute to the charges.